Good morning. In the first video, we talked about how perceptions can confuse the issue when we're trying to do physics experiments or make measurements. Today, I want to talk a little bit more about that sort of thing, but I want to talk about how we're going to fix it and how this is eventually going to lead us into some much more interesting topics. So let's talk about inertial reference frames. Previously, we've seen that if we want to do measurements, it's not appropriate to have one single individual doing these measurements. Ideally, at every point where I want to make a measurement, I will put an individual down. This individual will know what time it is, and this individual will not be moving around in some sense or the other. Let me be a little bit more concrete about that. Every individual that I'm going to have in my system here is going to be stationary with respect to all of the others. Also, each one is going to have a clock, and these clocks are going to be synchronized, not visually according to an individual, but actually synchronized. Also, we're going to assume that they're running at the same rate and they stay that way. I have to make that last comment because in view of the weirdness that's eventually going to happen, sometimes people will adopt the strategy that they just need to keep readjusting clocks to make things work out the way Isaac Newton would have thought. Doing that destroys the usefulness of the idea of a clock, so we really can't be doing that. Also, we will assume that Euclidean geometry is valid. You might take that as a ridiculous given, but, well, we'll see later. And lastly, I want Newton's first law to be true. For a given object, either a force acts on the object or there is no such force. Newton's first law says that an object with no force acting on it either remains at rest, if it was rest to start with, or moves in a straight line with uniform speed, unless there's a force acting on it. A setup like this, we're going to call an inertial reference frame, also known as an inertial observer. And here you have to be very careful with your language. When people say that, inertial observer, they don't mean any one of these individuals. They mean the entire collection of them. All of these individuals need to be stationary with respect to each other. This keeps us from missing the bus, among other things. Each one has a clock that is synchronized with all the others. Euclidean geometry is true. Newton's first law is true. The premise that we're going to begin with is that it's possible to cook such a situation up. If you have a group of people reasonably close together on or near the surface of the Earth, then this is approximately an inertial frame of reference. Although, as we'll see later, it's only approximately so. If you have an airplane full of people who are stationary with respect to each other, have synchronized clocks, if Euclidean geometry is valid inside the airplane and Newton's first law is true, that would also constitute an inertial frame, at least to a very high degree of approximation. The reason that I mentioned the airplane is because it reminded me of something that happened many years ago. I was on an airplane going to a math conference. Yes, there are math conferences. On the airplane, as we were approaching the airport, we hit a patch of air that was remarkably smooth. You couldn't feel any turbulence at all. Looking out the window, it looked for the life of me as though we were sitting still and it was the city that was sliding past underneath us. If you were in that airplane, in that situation, and you took a quarter out of your pocket, held it over your hand, and opened the other hand, you would perceive that it falls in a straight line onto your other hand. If you did the same thing standing on the ground, the same thing would happen to you. There's a thing called the principle of relativity that says, in an inertial frame at least, if I do an experiment, like dropping a quarter, the results of that experiment cannot depend on whether or not I'm moving relative to someone else in certain ways. Can one inertial frame accelerate relative to another one? Imagine I've got a baseball sitting around in three-dimensional space. Either there is a force acting on the baseball or there isn't. Now, this doesn't have anything to do with who's doing the measuring. Either there's a force acting on it or there isn't. If there isn't, then the baseball could be stationary or it could be moving in a straight line with constant speed. Let's suppose that we have this frame of reference in which the baseball is at rest. This could easily be done. If the baseball is not moving, we will just put our individuals down and have them not move. If the baseball is moving, say in a straight line with constant speed, we'll make all of our individuals move in straight lines with that constant speed parallel to the baseball. But then imagine another inertial frame, another group of individuals which obey all of our restrictions. If it were possible for the green inertial frame to accelerate relative to the brown one, then the green individuals would measure and report back that this baseball is accelerating, even though there's no force acting on it. This means that this can't happen if we actually have an inertial frame, because the green frame would violate Newton's first law. There would be an accelerating body that has no force acting on it. So the answer to the question is no. On the other hand, inside my airplane and on the ground, we at least more or less have inertial frames. Inertial frames can move with respect to each other, but they can't accelerate with respect to each other. So let's suppose I have an inertial reference frame. I'll draw 9 of its individuals in, indicated by the plus marks, which I'm drawing with a brown pen, but I'm not sure how well the colors are going to show up. I might have another inertial reference frame, which I'll indicate with X's in green, although I'm not sure how well the color green is going to show up. It could be that all of the green X's are at rest with respect to the purple pluses. If that were the case, I would just make the clocks on the green X's synchronized with the brown pluses, and basically I've just drawn in twice as many individuals as the original brown plus frame of reference. So that's not very interesting. We just established that the green X's cannot be accelerating with respect to the brown pluses because that would violate Newton's first law in the other reference frame. Therefore, each green X must move relative to the brown pluses with a constant speed and constant direction. Since all of the green X's are at rest with respect to each other, all of the green X's are moving in the same direction at the same speed as measured by the brown pluses. You could make that exact same sentence with the brown and green interchanged if you want. So let's represent that situation by drawing green arrows in at the green axis. This indicates how the greens are moving with respect to the browns. In relativity books, people will often act as though these people are isolated from each other and cannot communicate at all, which is nonsense. There's nothing stopping this individual from pulling his cell phone out and calling that individual. In fact, they could have a big conversation. If they did, they might say something like this: have you noticed that each of you is moving relative to each of us in the same sort of direction at the same speed? The other group would say, yes, we have noticed that. So they get together and they decide to pick a point to call the origin. Neither one of these two groups of individuals have yet set up a coordinate system, but looking at the situation, there's a certain direction that seems like it would be easier than other directions. So both the brown plus gang and the green X gang agree that their first coordinate axis is going to be this. You could have the brown X coordinate axis or the green one. I've drawn it in using my green pen out of laziness. Having selected an X-axis, the Y-axis will be at right angles to that and pass through the origin. This seems to be a natural way to set things up. So that I don't have to keep changing colors all the time, I'm going to call the coordinate system of the green individuals. I'll write them as X and Y with a little bar above them. The coordinates of the brown pluses, I'll just call X's and Y's with no bar above it. Even at this stage, there's kind of a psychological bias that people might be thinking that X and Y are the real important coordinates, and because these are X's and Y's with extra symbols, they are somehow less than important than the other ones. I could have called the green ones X and Y and the brown ones X bar and Y bar. This is just a way to keep which system we're using in mind. Suppose that you have an object and you measure its location using the barred system. Because of the parallelism here, the y-coordinate of the barred system is going to be the same as the y-coordinate of the unbarred system, but the other coordinate will vary. If I imagine that the speed of the green individuals relative to the brown individuals is v, v is for velocity, the plus network is going to see not just see, but measure using the individuals a point that's at rest in the barred coordinates will be seen to be traveling off to the right in the unbarred coordinates, in fact, this holds true even if the point P is not stationary in the barred system. Whatever the x bar and y bar coordinates of a point are, the x is going to change because of the motion. We are moving forward relative to the unbarred system at speed v. So the x coordinate of really any point is going to be its x bar coordinate plus vt. The y coordinate doesn't change because the y-axes, either in the barred or unbarred systems, are at right angles to the direction of travel. So y is going to equal y bar. People will often write this as expressions for the barred coordinates in terms of the unbarred ones. If x is x bar plus vt, obviously x bar is x minus vt. If y is the same thing as y bar is the same thing as y. These formulas are called the Galilean transformation. And in classical physics, pre-relativity physics, it was thought if you have two inertial frames, their coordinates can be arranged so that they're related in this way. And anything that you do as an experiment, measuring it with one set of coordinates, do the same experiment measuring the second set of coordinates. No important physical quantities can be altered because of which coordinate system you used. Imagine that you decide to use the barred coordinates. You look at some object, it's moving in a straight line with constant speed. A comma C is a point in the plane that the object is at some point or the other. These are x bar and y bar coordinates. B and D, for those of us who want to think of it that way, are the components of the velocity vector, and T, of course, is the universal absolute time. What does this look like according to the unbarred coordinate system? I can use these Galilean transformation formulas to figure out that using the unbarred coordinate system, the unbarred x is going to be a constant plus another constant times time. This is the same form as what x bar was. It was a constant plus a constant times time. Y is a constant plus a constant times time. In fact, y is the same thing as y bar. If you were to draw the graph of something like this, you would get a straight line. If t is the absolute time, then the derivative of x with respect to t would be b plus v. The derivative of y with respect to t would be d. The y component of the velocity is the same as in the barred system, but the x component isn't. The barred system is moving to the right at speed v relative to the unbarred system. In the barred system, x bar was increasing at a rate of b, so it makes sense that the derivative should be b plus v. Something that is stationary with respect to one reference frame may or may not be stationary with respect to another. What about acceleration? I'm thinking of having some object. It may be moving around with respect to the unbarred system, with respect to the barred system, or maybe both of them. How is the components of velocity and acceleration in one system related to those in another? Because of this fact, the derivative of x bar with respect to t is the derivative of x with respect to t minus the constant relative speed of the two reference frames. There's no vt term in this one, so derivative of y bar with respect to t is the same as dy dt. The components of velocity can vary from one frame to another when we do this kind of transformation. On the other hand, if you take the second derivative of x bar with respect to the absolute universal time, well, the derivative of a constant is 0, so you get the second derivative of x with respect to time, and likewise, the second derivative of y bar and the second derivative of y are the same. The velocity of an object can depend on which coordinate system you're using, which inertial frame. In our current circumstances, the acceleration doesn't, though. So you'll sometimes hear people say that in physics as understood by Galileo, velocity is relative, but acceleration is absolute. This will come back to bite us later on. Imagine a situation where you had an inertial frame represented by these individuals. There's another inertial frame, the barred frame, moving to the right at speed v relative to the unbarred individuals. An individual in the barred system moving to the right relative to the unbarred system, even so is a member of an inertial frame. His physics experiments are as good as anyone else's. So relative to the barred frame, the individual on the skateboard throws a baseball forward at speed u. Assuming that he throws it at t equals 0 at the origin, the x bar will be u times t, and assuming that we're far away from any sources of electromagnetism or gravity or anything like that, I'll suppose that the y-coordinate starts off 0 and stays that way in both the unbarred and the barred systems. Because of our previous comments, though, I know the relationship between the barred and unbarred coordinates. According to the unbarred coordinates, the object will be moving to the right at speed u plus v, just like you would expect. I'm not a historian of science, so I won't go through the long list of experiments that led to this conclusion, but in the late 19th century and early 20th century, a wide variety of experiments were done with light. Suppose that an individual of the barred system is moving along to the right with speed v relative to the unbarred system. He doesn't have a baseball, he has a flashlight. So he turns it on, and he and his friends in the barred coordinate system measure the speed that the light goes off into the distance as c. Based on what we were just saying a minute ago, the unbarred system should measure a different speed. The unbarred system says the light ray is going to the right at speed v plus c. This is what we expect. This is what we would get from the Galilean transformations. But something funny happened. After a lot of work, the conclusion that people came to was, experimentally, the speed of light measured by an inertial observer in a vacuum is always the same value. It's always the roughly 3 times 10 to the 8 meters per second. This is going to be our wedge into talking about special relativity. I hope everybody has a good day, and I'll talk to you again soon.